Great. Good morning, everybody. I'll just remind you where we stopped. So we covered the equipartition theorem, and then we looked on something that we call the Gibbs paradox, where Z for particles in a specific volume, and the gas was ideal gas, and we computed the partition function of one single particle inside this gas using this factorization trick. So we have many particles. All the particles are not interacting. We pick one specific particle. We compute the partition function of this particle using classical statistical physics, and we discovered something, and we take it to the power of n, and we discovered something which was unpredictable from the first glance, and this was that the free energy was non-extensive. Now, the problem with this non-extensivity is that it was our first assumption in this class that the energy and all the other thermodynamic potentials have to be extensive. Otherwise, nothing works. Absolutely nothing works. And Gibbs discovered this, and he used a correction in order to fix this non-extensivity. And the correction was to divide everything by n factorial. Now, why it is a paradox? The paradox is because the particles, although they are identical, in classical mechanics there's no such thing as indistinguishable particles. I can always follow them. I can look in the picture, taken at a specific time, and then I can follow each and one and single particles. Therefore, all the different combinations are not going to be identical. I can say where this combination came from and where that combination came from. Therefore, this is division and hand-waving argument why I have to divide it and why the particles are indistinguishable, but they are also distinguishable. Okay. That's the paradox. Now, the fact, mathematical fact, is it works. It actually works. You can compute everything is fine, you haven't broken anything, but there still stays this paradox of why to divide by n factorial. Okay? And now we are going to a little bit dive into this matter, why this division by n factorial works. And the answer is quantum mechanics. Okay, so when Gibbs devised this mechanism, it was the end of the 19th century. Nobody knew anything about quantum mechanics, but it shines from almost any aspect of physics in the end of the 19th century, beginning of the 20th century that you look on. You just have to look for it. Now, we know quantum mechanics, so we can look exactly what happens. So first of all, let's see what happens in a very simple problem where we have two particles. You can call them 1 and 2. And this is the classical perspective. Now let's assume that I have those two particles and I have two boxes, right? Now, how many different states, there are in the system? So first of all, I can put particle 1 in box number 1, and I can put on the left box, and I can put particle number 2 in the right box. So this is one state. Another state is when I put particle number 2 on the left hand side, and I put particle 1 on the right hand side. So this is another state. Other states in classical physics, well, all the particles are sitting on the left-hand side box, okay, and nothing is actually present in the right-hand side box. And the last state is where all the particles, number 1 and number 2, are sitting on the right hand side box. Okay, so those are, if I have two boxes and I have two particles, from classical perspective, I can only have 1, 2, 3, 4 states. Okay? So this is the classical perspective, 4 states. Now let's look on the quantum perspective. So for quantum perspective, we have, remind you, we have bosons and we have fermions. So look on boson particles. Bosons. Okay. Now in bosons, if the particles are identical, I cannot name them 1 and 2 or something else. Okay, they don't have names. So for this perspective, first of all, I can have the situation when one of the particles is sitting on the left, one of the particles is sitting on the right. Okay? Another state is when all the particles are sitting on the left and none of them sitting on the right. And another state is when all the particles are sitting on the right. Okay? So from the perspective of bosons, I don't have 4 states, I have 3 states. 3 states. Another perspective, and the last one, is fermions. Right? This is quantum. This is also quantum. And for fermions, the situation is even simpler. Right? So fermions, there is Pauli exclusion principle. They cannot occupy the same state. Okay? For me, the states are the boxes. So the only solution is one particle on the left, another particle on the right, and that's it. So here we have one state. All right, so now we're looking and we saying the problem is from counting states. That's what Gibbs told us. Okay? And the solution of Gibbs is you take all the possible states that you have in your system and divide it by the n factorial such that you can swipe everything back and forward. Okay? Because the particles are identical. You don't need or you don't have to do it not for fermions, not for bosons. Okay? And they said, well, your solution for classical system, 4 states, is wrong. So what you have to do, according to Gibbs, you have to divide the number of states by how many particles do you have? 2 factorial 2. So you take the 4, divide it by 2 factorials, and you get exactly 2. So what Gibbs suggesting? So Gibbs, we know that particles are either fermions or bosons. It's related to the possible symmetries of the Schrödinger equation and the solutions to the Schrödinger equations. There is nothing else. Okay? So you have to be either over here, either over here. What Gibbs is doing is neither bosons or fermions. You're somewhere in between. Right? You're somewhere in between those two. So you neither of them. First of all, you're not going too much higher because it's not 4, it's actually 2. And it's, you can call it, well, it's some sort of a compromise, yes? But it's not exactly so. Why it's not exactly so? Because Gibbs is actually way, way better than just saying I'm making a compromise between, I'm making a compromise between fermions and bosons. Gibbs is actually saying the following thing. When we're looking on high enough temperatures, and you have a lot of boxes in your system, okay? When you're looking on such situation, the possibility, whether it's bosons, fermions, classical particle, the possibility for large system, for high enough temperature, the possibility of getting 2 particles at exactly the same state is negligible. So when you're going to high temperatures, the probability that two particles occupying exactly the same state, when you have many states, okay, is actually negligible. So for high enough temperatures, high enough, this is negligible. Well, not two particles occupying exactly the same state for fermions in the first place. And then you can say, well, it's negligible also for the classical system. You can erase those. Okay? So what happens in all the systems when the temperatures are high enough? So instead of getting, for fermions, it's still one state. For bosons, you don't have three states, you have one state. Probabilistically, it's not that it's not possible to be in this state. It's just the probability of such an event is completely negligible, so we forget about it. Okay. Now, what happens for the classical particle? For the classical particle, if you neglect the possibility of two particles occupying exactly the same state, you have two states. Okay. And when you have two states, and you perform the Gibbs correction, you have 2 divided by 2 factorial, you're getting 1. Okay. So what exactly Gibbs is doing? Saying for high enough temperatures can be actually not so like 0 Kelvin, it can be 50 Kelvin, depends on the material. For high enough temperatures, when you neglect the possibility of occupying exactly the same state, fermions, classical particles with the Gibbs correction, and bosons provide you exactly the same result. Okay. So this is why Gibbs works, actually. But it works only for high enough temperatures. For low enough temperatures, the classical picture won't work because you need to actually take into account quantum effects, and you need to decide whether you are boson or fermion, because this will give you 1, this will give you 3, okay, and this will give you something else. This will give you 2. So low temperatures, Gibbs correction, because it's a classical system, won't work. High enough temperatures, all the 3 models provide you exactly the same result, and this is why you need to divide by this 2 factorial. This is the physical explanation. The resolution, of the Gibbs paradox. Okay, so if we mentioned already quantum particles, this is where we're going. Any questions? Yes.
Why in high temperatures the 2 particles have a negligible probability to occupy the same state?
Let's assume that you have many boxes. Okay. High enough temperatures, you have a spectrum is very high, you can occupy many different boxes, and the probability that 2 particles occupying exactly the same box is going to 0. That's it.
Suppose we have a 2-level system.
If you have 2-level systems, it won't work, yes. Okay. So only for systems that are large and you have many different states. Yes. Other questions? Yeah. So if we mentioned quantum particles, we're going to the field of quantum statistics. Quantum statistics. So we have to take into account whether our particles are fermions or bosons. Okay. Now let's look on the simple model system. It's not 2 states. Let's assume that we have 3 states. Okay. And I have epsilon 1, and I have epsilon 2, and I have epsilon 3. So this is the energetic spectrum of my system. Okay. Great. And the particles are fermions. And let's assume that I have 2 particles inside my system. Number of particles, n equals 2. And they have exactly the same spin. Okay, so I have fermions, they have exactly the same spin. When I have such a system, and I put one of the particles at the ground state, at the energetic level epsilon 1. So what happens immediately? If I put one of the particles at the lowest system, I know for sure, due to the Pauli exclusion principle, that the other particle cannot occupy this lowest energetic state, right? So it can be either over here or over here. Those are the two other possible states. Now, this will happen even if I'm assuming that my fermions absolutely not interacting. Okay? So there are no forces between the two particles, but still the Pauli exclusion principle, it's like a very hard, strong constraint that's present in the system. It always tells us if one of the states is occupied, you cannot put another particle over here. You have to put it either to the epsilon 2 or either to the epsilon 3. So even if the particles are not interacting, they are interacting. Okay? It's not a paradox, it's just the statement of Pauli exclusion principle. You don't care about some forces between the particles. The most important thing is the exclusion principle. They cannot occupy exactly the same state. So the particles for quantum systems, for fermions, for bosons it's a little bit different, but for fermions at least, the particles are always interacting, and not just always interacting. The interaction is extremely, extremely strong. Now, remember the problems that we dealt with when we met these strong constraints. Where we met this strong constraint? In the microcanonical ensemble. So what happened in the microcanonical ensemble? It's very simple, right? You just count the number of states that you are accessible to your system. You take a log of the number of states, you multiply it by K Boltzmann, this is your entropy, and then you take all the derivatives that you want and you solve the system, right? So solve the eddy problem in microcanonical ensemble. But why haven't we stick to this moment with the microcanonical perspective? Why, at some point, I told you, forget about microcanonical perspective, let's switch to the canonical perspective. There were two claims. One, oh, it's not so physical, right? Why it's not so physical? Because we're looking on the system, and when I'm looking at the system, it's in contact with all the other particles that are in the room. There are some interactions. I cannot assume, I cannot assume that any given system is a microcanonical system. I have to do it for extremely large systems. So that was problem number one. Problem number two, a much more technical problem, was the moment that we have constraints, hard constraints in the system, you are doomed. Why you are doomed? You can solve simple system. You can maybe solve, or you can solve two-level systems. You can solve, maybe, after hard work, three-level systems because you have to count all the possible configurations. Okay? You cannot say, well, neglect some of the configurations. You have to take everything into account because the constraint is extremely harsh. This was the case in microcanonical perspective. Remember, I had a specific energy and I had to fit all the particles such that the total energy would be exactly the sum of all the energies of all the particles, all the time. So this hard constraint makes the problem a very hard combinatorial problem. So maybe I can solve it for two states, maybe I can solve it for three states, but the moment that I have real physical problems where there are many states involved, I cannot simply deal with it. Right? Technically, I cannot solve big systems where I have always to consider hard constraints. I always have to keep in mind, no, I put this particle over here, therefore I cannot put here another particle. Something is really, really bad with this problem. So how we dealt with it in the microcanonical perspective. So what we have done is the following. Effectively, we assumed that the energy is not conserved, right? We just said, oh, we have a system, we have a heat bath, and our system can exchange energy somehow with a heat bath. So you had a constraint, and we replaced this constraint by some averaging, right? We just said, oh no, so the only thing that you know is the average energy or the temperature of the system. This is you keep constant. Everything else you do a specific game. The same thing we're going to do with this problem of quantum statistics. Canonical perspective for quantum statistics leads you to a dead end. Eventually, for a large system with hard constraints, you will be doomed to use only numerics because you have hard constraints. You have always to remember, no, I put one particle over here, I put another particle over there. Factorization won't work. Okay? I won't prove it to you why factorization won't work, so you have to trust me. But for any system where there are strong constraints, factorization won't work because it leads to very strong dependencies. Okay? So we need to invent another technique to treat systems with hard constraints in a similar fashion as we did for microcanonical ensemble. So instead of saying, oh, I will teach you some very crazy combinatorial methods, right? I told you no, we will switch the technique. Okay? We will look on the system from a different perspective. The same thing happens for quantum statistics. We're not going to do crazy combinatorics. Okay? We're going to look on the system and say, let's assume something and use this assumption to somehow go over those hard constraints. It's not that I can neglect Pauli exclusion principle. It's impossible, okay? Because it's a very strong interaction. But I need somehow to look on everything and say, let's modify something. How? So if in the microcanonical perspective, we modify this by saying the energy is no longer conserved, okay? Any statistical physics problem, except microcanonical ensemble, the energy is not conserved. You have no constant energy. You have some average energy, but the energy is never conserved. For quantum statistics, we need to assume something else. Okay? And I'll explain you exactly what we're going to use. So here, it's not just the energy is not going to be conserved, also the number of particles is not going to be conserved. Okay? And I show you now how we're going to develop this. So, in order to do so, we need a technique of how we generate ensembles. Right? We started from microcanonical ensemble, and then we hit a wall, and I said, let's develop another ensemble, and then we developed a canonical ensemble. Okay, so here we hit with the canonical ensemble another wall due to the constraints, and I'm going to say to you, let's develop another ensemble. Right? So instead of saying, let's develop a very specific ensemble that is tailored specifically for this problem, I'm going to teach you how to develop any possible ensemble. Okay? So if you treat or you sometime in your life stumble across a problem, for example during an exam, where you need to develop another ensemble which is not microcanonical, not canonical, not grand canonical, that you have the tools to develop any ensemble that you want. Okay? And this is all related to probability and entropy, how to develop ensembles. Okay. So this is what we are going to do. We're going to talk first a little bit about what is entropy for the microscopic perspective. And we use the principle of maximum entropy to develop any ensemble that you want. Okay? So what kind of entropy we have seen so far? We have seen two kinds of entropies, right? So first of all, we have seen that dE equals TdS minus PdV. And here, the entropy entered as in thermodynamics something very general, something not clear, and I had to tell you that there is a principle, the second law of thermodynamics, about the principle of maximum principle of entropy, and I know that the entropy grows as a function of energy, and I know that it's concave. Okay, so general principle, but I have no idea what entropy is. The second time that we met entropy is when I told you that entropy is K Boltzmann log the number of states of the system. Okay. And we use this formula. I haven't taught you where I brought it from. I just waved my hands that, oh, there is extensivity and there is a entropy have to be somehow, well, the number of states is also somehow grows geometrically, so let's take the logarithm of the number of states, and this is our entropy. So why? How? Okay. But this is what we used in microcanonical ensemble. Ensembles. What I'm going to do now is to use this in order to somehow develop a more general principle for the entropy. Okay, so how we do it? We have to start with the ideas of Ludwig Boltzmann. The same Boltzmann for the K Boltzmann. Entropy by Ludwig Boltzmann. There are two ends of them. Okay. So Ludwig Boltzmann believed in gases and what you can learn from gases. So he started from this, which basically the first law of thermodynamics. Okay. So dE equals to TdS minus PdV. And he also used the ideal gas equation. So we have PV equals to N K Boltzmann T. Ideal gas. It's the simple system, and you always start from it, and you try to see where it takes you. Okay, so let's see what happens for the ideal gas. So first of all, I'm going to use this equation. From this equation, I'm going to see what is the entropy, and afterwards, by substituting this equation here, I'm going to try and obtain something more like an entropy for an ideal gas. So what happens over here? So we have from here that ds equals to 1 over T dE, okay, plus P divided by T dV. Now, I'm going to use the fact that dE by dt equals to CV, okay. Therefore, ds equals to CV divided by T dt plus P divided by T dV. Okay? And I'm going to use the following physical perspective. So this is the general equation. Right? I have a system where I know the heat capacity. I can measure the difference in the entropy by knowing what is the heat capacity, what the temperature, what the pressure, what the temperature, and measuring the differences in the temperature and the differences in the volume. So let's assume that I have a gas. Okay. I have a gas in a chamber, and the volume of this chamber is V1, and by keeping somehow the temperature constant, let the particles from this chamber on the left hand side expand and occupy the whole chamber, which has the volume V2. Okay? Now during this expansion, I assume that T is constant. Okay? So what happens for this case? So when T is constant, I know that ds equals to P divided by T dV equals to, I'm going to use the ideal gas. So instead of P, I have N K Boltzmann. Sorry. N K Boltzmann T divided by V T dV, or ds, I cancel T and T, ds equals to N K Boltzmann d log of V. So delta S, which is S after all the gas expanded to the total volume F, V2, minus S, the entropy at the initial state before the gas started to expand, equals to N K Boltzmann log of V2 minus N K Boltzmann log of V1, or delta S equals to N K Boltzmann log of V2 divided by V1. So all of this is the thermodynamical perspective. Very simple, works for ideal gas. Great, great, great. Right. Very simple formula. Now it is of course not enough, because remember, we want to talk about states, we want to talk about probabilities, etc., etc., etc. Now, let's look on one single particle. Okay, we still have our chamber. And the single particle sits somewhere inside. This is our single particle. Now, remember, there was some membrane that we deleted, and this is volume V1, and the total volume is V2. Now, I ask you the following question. What is the probability to find this one single particle inside of volume V1, wherein there are no chambers whatsoever, no membranes whatsoever? So the probability to find this particle on the left hand side is called P1. It is V1 divided by V2, and that's it. All the volume that's accessible to this particle is V2. I'm asking about the probability to find the particle in the volume V1. I assume that the probabilities are homogeneous. Okay, therefore, it's the volume that I'm asking for divided by the total accessible volume. So this is the probability. Okay. Now, let's assume that I have, instead of one particle, I have two particles. Okay. So then I can ask you, what is P2? P2 is the probability to find two particles inside this volume V1. So what's the probability for this event? They are completely independent. This is an ideal gas. They don't see each other. They don't care about each other. Okay? So we can take this as independent random variables. So the probability of the first particle to be in volume V1 multiplied by the probability of the second particle to be in the volume V1. So this is V1 divided by V2 multiplied by V1 divided by V2. It is V1 divided by V2 to the power of 2. Call it P1 V1, P2 V1. Now we can continue this as long as we're dealing with ideal gas, we can continue with this, okay, and we can, question? Yes, no? No. We can continue with this and add additional particles, okay? And then I can say, well, the probability of n particles, it's ideal gas, no matter how many particles I add in, they don't care about each other, okay, so the independence still sticks. So Pn V1 equals to V1 divided by V2 to the power of n. Okay. By the way, what is Pn V2? What is the probability of finding n particles in the total volume V2? 1, of course it's 1. Very simple. Okay. Now, I want to connect those probabilities. Somehow, you see I have a fraction, V1 divided by 2. Here I have V2 divided by V1. So I want to connect those probabilities to the entropies. The entropies that I have over here. So how do I do it? So first of all, let's look and say, well, what is log of P1 V1? So it is simply n log V1 divided by V2. What is log of P2 V? Or P or n, P and V2, it is 0. Okay, so we have some sort of connection. Therefore, I can write the following. The logarithm of Pn of V2 minus the logarithm of Pn over V1 equals to minus n log of V1 divided by V2. Now this is already very close. See, delta S, log V1, V2, V2, V1. Okay. So, what do we have over here? So, what we see is that delta S equals to minus n K Boltzmann log V1 V2. Do you agree with me? So delta S, it is n. So we have, it's only K Boltzmann multiplied by log P n V1. So we managed to somehow to connect those probabilities. Have I switched something over here? There should be minus, right? No? Okay.
Yes, it should have been minus logarithm.
Yeah. So there is minus over here, right? Then I can say the following, or Boltzmann said the following thing. S, if we start from some specific entropy, okay, and we call this level of the entropy as 0, which is just S0. S is minus K Boltzmann log of the probability of the state. Okay? So if we're looking on a specific system, like the ideal gas, and we want to compute the entropy, okay, the only thing that you need to do is to say, well, let's take the probability of being in this state, of this specific state, okay, take a log and multiply it by minus k Boltzmann. Now what happens in ideal gas or any microcanonical system? P is simply 1 divided the total states in the system. Okay. So if omega is the total state of the system, the probability of a specific state is 1 over omega. We can say that S is equals to k Boltzmann log of the number of states inside the system. So you remember this formula? I waved my hands, said, well, there's exponential growth, we'd have to take the logarithm, etc., etc. But if you start from a very specific system, like the ideal gas, where anything, all the different states are exactly the same, probabilistically exactly the same, because everything is homogeneous, okay, you obtain that the total entropy of your system is this formula, which is k Boltzmann logarithm of omega. Okay, that's it. You don't need any hand-waving arguments. You don't need anything. Right? You just say, all right, I'm using the first law of thermodynamics. I'm properly computing the probabilities. Okay, I'm properly computing the probabilities by saying where the particles are located and what are the location or the probabilities of the different particles. Okay, and from this perspective, you connect the entropy to the number of states of your system. Okay. Now, what is more important is actually this. The entropy is connected to the probabilities. Okay. So great, we've done it, and we use this formula for the microcanonical ensemble, right? Now we can next ask a different question. So for canonical ensemble, we did something else. We allow the system to exchange energy. And how I describe it to you probabilistically, I said, well, now instead of computing regular probabilities, let's compute conditional probabilities. So what I'll do tomorrow is to obtain a more general expression for the entropy by using the probabilities from the canonical ensemble. Okay? So this is great, this works, but how we can generalize this expression for something which is not microcanonical ensemble and not ideal gas. Okay? This was the next step. This was the entropy by Boltzmann. The next step is going to be entropy by Shannon, which is much more general expression that we have over here. And this general expression, this what will lead us to general ensembles. I will see you all tomorrow.